dominated arena, but you know, the images you produce are very inspiring to further the discipline of space architecture. And you're right, it is the ultimate interdisciplinary activity that we all like to think about.
Well, there are also two things. Yes, of course, it's still very much engineering-oriented field. I have in the class, it's always a mixture of architects and engineers, and that is very helpful for both. And again, as I agree with Barbara, so creativity comes, it's not really related to the discipline. What they do learn from each other, it's a different point of view. And of course, some skills as well. But this approaching of the problem solving, defining the problem, and that is the major thing, because that is a very important skill, and not everyone can do that. Finding where the problem lays. Defining the problem, you're already halfway done, but where to start is it's really critical, right? So independent thinking and all of it, so it helps them to also respect each other. And I think that is, again, when they start working for the industry, it's changed paradigm. And it's been changing already. So as I said, so many students now, graduates, are working for the industry and different companies. And now they're posting and accepting degree and understanding space architecture. So at least it's not something like, whoa, what is that?
Thank you, Olga.
Thank you very much, Olga. And I would like to invite Sam Jimenez to turn on the camera. Hello, Sam. Hi.
Hello, how you doing?
Hi, Sam Jimenez is a space architect with over 30 years experience in the aerospace industry with NASA, DoD, and international space programs. He is currently CEO of Exploration Architecture Corporation, a space architecture consulting firm he founded in 2007. In 2023, he was induced into the San Antonio Aviation and Aerospace Hall of Fame. Sam, you may share the screen.
Okay, thank you. There was a question earlier in the day about anybody online that knew Buckminster Fully. And I didn't know him, but I did have the pleasure of meeting him when he came to visit our university. And he was very mesmerizing, and he did definitely have a language all of his own. Everybody was just hanging on his every word. So that was a great highlight of my life. Okay, so let me get the screen up.
Mm-hmm.
And, so let's see, I have a video. Won't let me share the sound.
Okay.
Is it possible on your side? It's not great out on my side.
It should be possible, yes.
Sam, are you saying that you met Bucky?
I did meet him.
This was during Geet, Trotty, and Bell?
No, this is way before that. This is back in
really? Okay.
back in my undergraduate days.
Oh, fantastic. Okay.
Yeah.
Sam graduated from SIXA a long time ago, right, Sam?
Because I don't know if they may be.
I was the first class of graduates out of SIXA. There were three of us.
I see. And you know, there may be newcomers here who don't know that Buckminster Fuller was the one who framed the term spaceship Earth. And I mean, it's really a paradigm shifter in our thinking, I think, at that time. 1968, right? The operating manual for spaceship Earth.
Yeah.
69 or 68. No,
Hey, I'm trying to the share sound on the Zoom, and it's grayed out. It won't let me share the sound.
I think when you share the presentation, the sound should go automatically.
Okay, we'll try it.
You haven't shared your presentation yet. All right, now you're sharing screen. Just a second. We don't see nothing yet. It's just a black screen so far. All right, we see it.
There
Yes, we see it.
Okay. Okay.
All
So
right.
usually when the sound is needed, that you click a button earlier before, but let's see if it works or not.
Let's see if
Okay.
it works. I think it
Yeah.
will work. Yes.
Okay. Let's see. So I'm going to talk about lava tube caves, and my goal here is to get Brant convinced that it's going to be useful.
They're
Okay.
laughing, Sam. Go for it, my friend.
Yeah, go.
That's my sole goal here.
Yeah.
So, all right. So,
Persuade.
I've been looking at lava tubes for some time here. I commissioned this piece of art from the renowned space artist James Bond to do this, and he got a little fanciful in showing a hollowed out lava tube that's been cleared out and ready for for construction. And there's the folks there. I guess they're in a pressurized environment because they're not in a space, but we've got a dome on top of it. And anyway, it was just kind of a thought experiment here to look at what's it going to take to actually look at these lava tubes, and how would we actually get there to utilize them. I don't think that's going to happen until very much later into the future, far future. Probably by the end of the century, we'll have a place where we have a thriving community. I'm going to talk about settlement here. We haven't talked a whole lot about settlement in sort of the city planning type of aspects. A lot of it's been today on the actual modules and point smaller habitats. But let's talk about the ability to actually create a thriving community and a settlement. But before that, there's a little bit of a commercial. Space architecture that I've been doing for some 30 years now. I began my company in 2007 as XARC, Exploration Architecture Corporation. We've done projects for all three planets, Mars habitation, of course, the lunar-based stuff, and even space stations and asteroid capture. Those are the domains. The one domain we've not talked about today is the terrestrial space architecture. How do space architects employ themselves here on Earth? And one of the things we really have focused on is the spaceport design. We've been part of the first commercial spaceports when it all began back in 2005 or 6, I guess, was whenever the X Prize was won, and Burt Rutan won that goal. And then Richard Branson decided to make a business out of it for space tourism. He's still trying to get it to happen. It's been a while, but we were on the design team that did with the Foster and Partners out of England, that did the commercial spaceport in New Mexico. We were part of the driving force actually for the Houston spaceport with our economic business study and our conceptual designs for what that would look like, and selling it to the city of Houston. To convince them that was going to be a viable project, and it's become very successful. Everybody from Houston knows, has been there. It's where now they've got Axiom and intuitive machines, and a lot of the whole deal about the spaceports is not really about the air side of the spacecraft. It's about the land side. It's the real estate development project essentially, and the attraction of jobs and growth in high tech industries to be part of that that driving force. Called the spaceport with the community. Our most recent project is with the government, with the U.S. Transportation Command. These are the folks that deliver the cargo and the material and the logistics for the military, forward deployment bases around the world, and all those logistics and humanitarian aid that happens whenever there's a human disaster. There's a program now currently called Rocket Cargo. This is the Elon Musk's Starship program is driving this as the benchmark, where they're trying to get a rocket around the globe in under an hour. But what happens, everybody's focused on the rockets, but nobody's focused on the infrastructure and the logistics to go into that. And what we're studying with the U.S. Transportation Command is the spaceport infrastructure that's going to be required globally around the world in the strategic locations that they would have to be at. As well as when a rocket has to go to a contested area or even an uncontested area, or where there's maybe an earthquake, that's happened. It's got to land somewhere to deliver its humanitarian cargo. How does it land in an unimproved surface? So we're looking at, we have some Air Force money to look at the temporary landing pad and the expeditionary type of deployment of landing fields for these rockets as well. So that's what's the area of terrestrial space architecture. It's still a very, very valid domain of the discipline. All right, let's talk about the lava tubes. So we know there are pits and caves and skylights. Skylights or the collapsed lava tubes in all three planets, all the planets essentially. It's a very prevalent geologic feature. The largest one here on Earth is the corner down the bottom there on the right side. That's the cave in Vietnam, Hang Son Dong Cave, and it's about 48 meters in height from the ceiling to the roof. You can see a small little man there at the bottom, in the middle of that picture. There's the ones on Mars are larger than the ones on the moon. The ones on moon are larger than the ones on Earth, and that's all because of gravity. We've discovered over 200 caves, or not caves, but these pits essentially. Some of them at the bottom of them are again these skylights, and at the bottom of the lava tubes. Some are just basic just pits. But we decided to look at this in terms of a case study. We took one specific site and called the Marias Hills Volcanic Complex at the Marias Hills Volcanic Complex. And there's a skylight there, a pit, and we wanted to use that as a case study, a benchmark, so to speak, to develop what we call our lunar or LEAP 2 program, or lunar ecosystem and architectural prototype. The technologies and the applications of how you get to these locations and how you develop them would probably translate to almost any one, even from the ones on Mars as well. So that's why we call it the prototype, like architectural prototype. What we found in the Marias Hill skylight, it's about a 60 diameter meter hole, about 140 feet deep. And what we're trying to do here is see what it looks like to develop this particular site for mining, for human settlement. How does human settlement actually begin at this particular site when it's a pristine location? It hadn't been touched for billions of years. How do you begin that process to establish it for whatever goals you have for the settlement, whether it be for tourism or for mining or for archiving of the human civilization's treasures or whatever. There's all kinds of ways you could utilize these sites. The goal would be, and this is the hard part, way down and part of the end of the decade before we can try and cover these holes up, put a dome on top of them, so that we can get out of these spacesuits, get out of the cans, and start breathing better air. But I'll talk more about that and that challenge in itself. So when you start looking at the site itself, and it's just like any architectural project or an urban planning or city project, you got to look at the site overall. How you're going to lay it out, where it goes where. In terms of you've got to have a spaceport. It's your first infrastructure that you need to create. You need to have a location for your power system. In this case, we'll probably certainly be using nuclear power, and then with the combination of solar power. You're going to have a mining site, your habitation zone. These are all things that need to be considered when you start. And then I'm saying over here in this. I guess you can see this cursor here. Yeah, here we go. These are storage tanks for if the business of the settlement is to maybe mine the ore, the regolith, extract the oxygen out of it, and produce it for fuels to sell to coming and going spacecraft that are going on to Mars, or just the general cislunar economy that's going to be developed by the time we get to this sort of a infrastructure development. And most certainly you're going to be mining at this on the surface for your oxygen requirements that you're going to need to have for the gases you need to have to breathe in your own environment down in the for the pressurized cave and the covered up dome as well. So at the end of it, you probably have something like this. So this is kind of another fanciful look at what this could probably look like by, I'm going to take a guess here, end of the century. You have as much surface activity as you do on the top of the location as you do underground in the lava tube. So, and of course, as you know, the lava tubes are going to be useful for the radiation protection in micrometeorites and, just a benign environment. It's a constant temperature there that you don't have to deal with on the surface between the diurnal cycles of hot and cold on the surface. So you have different technologies that would a little bit easier to design to than you would on the surface. But you see here, we're talking about a huge volume. Whether you can pressurize these, this or not, that's all not TBD, to be determined. But we're talking about technology development. 50 more years of technology development and materials development. Who knows what's going to happen? But between now and then, to allow this sort of a environment to occur. You see the landing port back at the back over there. That's the first infrastructure that has to be required before we even get down in the cave. You're going to be doing camp out missions and whatever, but you need to start to be, in terms of a full settlement, you need to get a landing port built, and that's going to allow you to be able to come and go with resupply missions and crew changeouts and all that goes into it. Over here we see our solar panel location, and on the other side of the terrain here is again the nuclear power system, and again there's a lot going on the top as much as there is on the bottom. On one side you have of the cave, since it's a lava tube, you have two entrances of the hole. On one side you have the industrial area, the production of the fuels or the air or whatever, or whatever the business of the community is, what's the export business of it, what's that economy that's being developed for it, the hydroponics and the growth of the farming. On the other side you have the habitation area, and I purposely designed this so that not to put modules, and that how do you give the imagination to the general populace that we can live the same way on the moon as you can on Earth. And these are again very fanciful in terms of what this could look like. You have your industrial area going on over here. This is again your storage and all the industrial zone essentially. So how do we begin this thing? How does that happen? How does that pristine site occur when there's nothing there? It's a phased approach. We know that now, between now and in this decade, we have the orbiting satellites that are doing the sensing. They're locating the topology, the minerals for the mineral. Maybe there's the ore field there where all the best regolith is, it has the best source of oxygen. We know that oxygen is in the grains of the regolith. And just an aside here, space architects, if you're going to go back to the moon, you need to know about dust. You need to know about lunar dust. You need to know about the grain sizes. You need to know about that if you're going to use regolith as a building material. It's very critical. So understanding that for remote sensing is going to be the first stage of the head. These are data sets that we acquire in order to convince ourselves this is a good site to go to. And then to go to it is going to be the robotics reconnaissance missions. These are for the scientists. The scientists are going to go there first. These are going to be pristine sites. Their measurements have to be uncontaminated by landing spacecraft that brought it there. So there's some issues there in terms of the traverses and how far away you need to land before you get to the pit itself. Then you need a way to get down into the pit. You need access. And there's all kinds of concepts out there, from zip lines to other type of robots to falling and propelled vehicles of some sort. But no matter how it is, you need to have a way to get down into it, and it's dangerous because there's a lot of collapse, a lot of rubble, a lot of debris. The next phase is going to be the human robotic reconnaissance, humans and robots. So I think by the end of this day, we may be able to see a mission to this lunar cave. Our LIDO mission is what we're proposing. But after that, then would be getting the ground truth from the robots that with the astronauts. The astronauts come and they'll do a camp out. It's going to be a small, short duration mission 30 days or what, just to bring in your provisions. You haul it in with your mule robots, and you just, again, ground truth what the robots that came before you found out, and see if this has really got the structural integrity. It's got the ability to put in the investment for the infrastructure that's going to be required for the long-term settlement of this particular location. Then by the mid-decade, I think we'll probably find a little bit longer stays. We can bring in some modules to stay there months at a time. You still got to deal with bringing your resources with you, your food supplies and your air and all this. There may be initial mining happening at the top on the surface. Again, on the surface, you've probably already started your spaceport, your landing pads that you need to have. So after that, but this is, I think, 2040, 2050 timeframe. Then after 2050 plus, then you start doing the full-blown infrastructure where you start clearing out the site, the debris, and putting in long-term, big heavy-duty power systems, communication systems. You got more ability to come and go with the spacecraft. By the end of the decade, maybe you do have this covered up dome at this point. That's kind of the goal there, and we're thinking we can get we designed this right now for a community of 100 settlers. It's probably at the most I think my viewpoint that we could be able to deal with the ECLIS requirements. They're going to be horrendous. All the resupply, the gases, the breathing air. Where does it come from? This particular pit probably requires almost 83,000 cubic meters of gas to breathe. And that does not include the tubes themselves. So that's the end of the century. So that's what we call our lunar ecosystem architectural prototype, the LEAP-2 program. All right, so the LIDO mission. So how do we begin? So we're actually looking at how do you actually do this? We're actually designing our mission concept for that first reconnaissance mission, and the way to get there and start exploring the cave. So we've come up with this mission called LIDO. LIDO, as you know, is the mother of Apollo and Artemis, and when she was pregnant, she was looking for a place a refuge to have her twins, and this is kind of named in terms of after her for that regard, in terms of maybe the settlement site is the birthplace of a human settlement. So I'm gonna play a video here. I hope this sound comes on, because it's really important to have the sound. Let's see if this works. Are you hearing sound?
No.
Yeah,
No,
no.
unfortunately.
No. Go to more on your Zoom menu. Go to more. There should be share computer sound.
Record, captions, raise hand, video.
The more. There should be a more.
Yeah, I did more. And the pull down menu says record, captions, raise hand, hide video panel, hide floating controls. There's nothing else about that.
You should.
I also cannot find it.
Let's see. Let me pause the share here.
Mm-hmm.
Try it again. So I'm going to try the share, because usually when you do the share, there's a little button at the bottom that says share sound. It's there, but it won't click. It's grayed out. I don't know why this is doing that.
Is there a separate permission for sound sharing?
No, that's too bad. Well, I guess I'm gonna play it, and maybe I'll narrate it as we go through.
Maybe if you go when you share the screen, do you go to basic or advanced?
Oh, good question. Let's see what I did.
Click the share screen again.
Yeah.
And then at the top you can see basic, and then you just click on
There.
advanced right next to it. And then try to click on video as to share the video.
Video, okay.
And maybe now should be better.
Yeah, still won't let me share the sound though. All right, let's see what it says, what it does.
Mm-hmm.
No, it wants to locate a video.
Or you send a link in the chat to Alma, and she can play this. It looks like a YouTube video.
Okay, I'll send you the
I
link.
can try, yeah.
Yeah.
Mm-hmm.
Let me get the link then. Let's see. I'm still sharing or not. Yeah, let's see. Let's go here.
It's open.
It looks like it's an online YouTube video.
Yeah, yeah. Do you have it?
No. I mean, we can see the screen that you're sharing.
Yeah.
It's loading.
Loading up.
I think it's better Alma share it. Alma, you can either do the search on YouTube, or Sam, if you click that upper left name, you'll go to YouTube directly. Then you will have a link, and copy that link in the chat for Alma to copy.
Yeah, let me get to the link. I'm sorry, I apologize, guys. This is big snafu here.
Can you tell me the title of the video? So if you cannot share the link. All right, I see a link here.
Yeah, Frodo seems to found it.
Oh, okay.
So Alma,
All
can
right.
you try?
I will try to find it now.
To my.
Okay, just a second.
If you Google.
Frodo, copy and paste the link in the chat.
Mm-hmm.
Alma,
Can you see the screen?
Yes.
All right, just a second.
It's the same one? It looks like it is. No sound.
Is there a sound?
Yeah,
No.
there should be sound.
We didn't hear any sound here.
You didn't hear any sound?
No.
Oh, man. I do have my own sound issues. This is why I'm on two accounts.
Let me try.
But I don't know if it has anything to do with it.
Okay,
Sorry.
Let me try it from my end.
Ken, you gotta pay $5 with the sound.
$5?
For sound.
Your speakers off.
It's Google.
So I put in the chat the link there. Well, okay. I don't know what's wrong with the sound. Who's playing the videos from you, from your side?
Okay, that's the best resort. Let's do it here. Yeah. Chat. Okay. Can you hear? Okay. Can you hear?
I don't hear anything.
Okay, 1 second. How about now? Can you hear?
No, not really.
No.
No.
You might have to give up at some point, Ken.
I know,
Yeah.
I
You
agree.
might have to concede defeat. I know it's terrible, but.
Yeah, you're right. Yeah. Don't know why.
It wasn't meant to be.
That's a good
Robots
point.
gonna go explore the cave.
Yeah,
Right.
technology. All right.
You can turn captions on a YouTube video
Caption.
if we just want that.
All right. So I think we do our best. So I think we'll just proceed to play the video. That's probably all we can do.
Yeah, I'll put the link in the chat.
Okay. We'll just,
Everybody
Yeah, or maybe if you put the microphone next to the speaker.
okay.
No, no sound.
All right. Well, we're gonna give up. All right. So let me try and narrate it, I guess. The idea is that this lander lands at some distance away from the pit because we want to not contaminate it, and so that it has an impact on your design of your rover. It's at least a kilometer of traverse. And we don't have any rovers that have traveled that far on the moon, of course, in a short period of time. And then the idea here is that we use the zip line concept to lower a payload down into the cave, and this taking lidar measurements of the cave pit itself. It then deploys a robot, a mule robot to go into the cave. There's actually two of them. One is the lead robot that does it's got the instrument payload on it, and is using it to map the cave out and take a 3D point cloud so we can understand the interior shape and geometry of it, plus also other measurements, mass spectrometry and other kind of scientific measurements that we want to take. And then it runs out of juice. So then now this other robot is tethered to the zip line. That's a smart zip line. It's receiving power and communications and data back to the lander. And it also has an arm on it that can allow itself to unsnag itself in case it gets snagged in rocks and whatnot with that cable. The reason we need to do this is because once you're in the cave, there's no communication. You don't have any relay to get a comm out back to line of sight to the Earth or whatever, or even to your spacecraft. That's why we're using this cable concept. And then so they do a tandem trade-off here in terms of this kind of a battery bot, we call it, the second rover, that it repowers that first rover so we can go on to another length of distance. And then it comes it goes as far as the second rover's cable will allow it, and then it can go then the first one can go even further, more down the road. Eventually it transfers its data to the other robot going through the cable, and then it be able to transmit your data back to Earth with your line of sight. And then by the time they finish their mission, they power down, and they stay there. They're not expended. They just stay there until the next mission comes. The human reconnaissance mission happens, to continue with their usefulness as a essentially mule robots carrying things. Then we're setting up, like you saw in the other still images, we're setting up the inflatable, the module that's inflatable. Then we began building the surface system, and for the building of the base on top, the lunar part on top. Here again, we're at the end of this, starting to get to the point where we can start creating the dome and building it out, and then we're now long ways into the century here by the time we get here. And now we have an environment that's that's breathable, and then that's it, essentially that. So sorry about that. Some snafus with technology. I'm going to take the screen again and finish up real quick here. Now you can see the screen. My side again.
Yes, we can.
Okay. So the next step here is to actually we're going to have a mission this summer into a local cave here in San Antonio called Kikaku Cave, and we're going to run a Boston Dynamic robot and put our instrument payloads on there and mount them on there and do some LiDAR measurements of this cave, just to do a ConOps of a mission scenario, how this could work out. So that's kind of an ongoing project we have. This is done more with our STEM education program that we have in San Antonio, where we have students that go through our program called Lunar Caves Analog Test Sites. It's teaching middle school through high school students about space exploration and advancing them into a career in space and aerospace. And this is one of the programs that we provide them with as well. So I want to talk a little bit about the construction aspect of this. When we talk about and this will be real quick, we talk about the building up there. We need to think about how do we build. The subsidiary of XARC is Astroport. They're doing the space construction material and manufacturing. Think of XARC as the architects and Astroport as the civil engineers. And we're doing all the geotechnical engineering that's required for understanding how to do the site preparation in the bulk regolith movement. We're talking about moving massive amounts of regolith to build these bases and build these landing ports, somewhere in the order of 50,000 cubic meters of regolith. That's a huge job, big for any Earth project. And we only have these little small tractors right now in terms of these bucket drums that are being used and developed by NASA. So we're going to need a fleet of these things to start moving this regolith. That's part of what we're looking at as well. We're doing a study for NASA on the site preparation for landing pads. How do you build a landing pad? How do you bring all that regolith together and use it as feedstock for our melting process that we use for making bricks? We have a process here where we're making this is shown, by the way, the blast zone, the blast burns out of bags that are contained with the regolith. But we're at some point we end up with the port. So we're using regolith as our base material. That's what we need to understand, is how to use that and use it for the construction aspects. You also can take the regolith and extract minerals out of it, metals and trap gases, like I mentioned earlier. We want to get to a point where we're building these bricks, these rebars, and building materials, that whatever we can find, and the usefulness out of the regolith simulant. This is a simulant you see here in this picture. We're taking an induction furnace and melting it, turning it into bricks. These are our test bricks we've been working with. And you see there in the middle of the screen, the vacuum that we're starting to learn how to make the brick in vacuum, because we can do it pretty well in ambient, but doing it and melting it in vacuum is a real challenge. So we were only able to do that. It took us almost a year to get it figured out. We just got our first vacuum brick in December. Now we're moving forward with that to get to the shapes we want to get. We're trying to develop what we call our Lunatron printing system, where it's a 3D type of print, where we feed the robot with the regolith, we melt it, it forms it, and it places it all at the same time. That's the technology we're developing. You can see here our first prototype nozzle that we developed to do that. We just getting to the shape we need to have in terms of these interlocking bricks. We haven't got to the size we want to get, because it's a matter of volume of melt and the way and the ability to cool the melt and cool the brick so it doesn't crack and you have a good sturdy brick. We've been able to get these bricks stronger than concrete. They're sturdy and durable. You can see this is our lab here with our vacuum setup. You can see in here we started putting the dirt in our, we call it dirty vacuum now. Almost done. So this is the zip line stuff we're working on. This is the inflatable floor system idea. Here's the regular pressurization stuff. We've been looking at how do you what's the porosity of the regolith, so that if you do get to the point where we can cover that dome, is it going to leak out at some point? And we're studying those kind of things. So these are all very nascent technologies, very nascent investigations. We got a whole century to figure it out. Thank you very much.
Thank you very much, Sam. There is a question. I'm going to read it to you now. And I would like to keep short with the questions and answers, please, because we still have more presenters to present their presentations. All right, and it's quite late in Europe. So a question from Esther. Sam, is there a structural support plan for the lava tubes to ensure the walls/ceilings will not fall? Lava tubes are not necessarily safe on Earth. At this site, there would be landing and launching that generates shakes and additional forces on the tubes.
Yes, exactly. That's the reason for the reconnaissance missions, is to see if what's the structural stability of that tube. And that, you know, first of all, you know, the openings was a collapsed skylight, so it collapsed at that point, right? So it was not very sound there, and it got a big rubber pile going into it. So how much structure is going to be required to understand, you know, the ability of this to make that investment in that infrastructure? So we don't know that right now. But that's the reason for the reconnaissance mission, is to do those characterizations.
All right, thank you very much. Can we move on with the presentations?
We have a question. One question.
All right. Okay.
Yeah, Sam, very impressive presentation. I had one quick question on the paving bricks units that you're using. We know that on regular terrestrial rocket launches that the flume can actually knock bricks and things like that loose. Is there, do you have some kind of way to mitigate that, or what's your plan?
Yeah. That's actually our proprietary technology that nozzle I showed you does. The way it works is that it's an actuated wall nozzle. So the nozzle is in the shape of the brick, that hexagonal shape I showed you, that trilobe. And as the first brick is placed, it moves to the next spot for the second brick, and the wall of the nozzle that's adjacent to the first brick raises up, and then that first brick becomes the formwork for the second brick, and so on for the third and fourth brick. So now those bricks, because they're hot and essentially molten lava, they've melded together and they've centered together themselves. So they form a cohesive pavement over time. And then we come back around and put a laser on top of the surface. We laser seam the edges as well. So that makes the pavement that we want to have, a cohesive pavement. But there's a lot that goes into it. We need to figure out the underlayment, the foundation. We can't just put the brick right onto the regolith. There's a thermal shock issue that's involved. So we have to figure out the underlayment of how that brick gets put on top of it. That's after it's been leveled out as well.
Thank you. Sam, I like lava tubes, you know that, right?
Yeah,
so
yeah.
I would only suggest that you consider Mare Tranquillitatis pit as opposed to the one you showed.
Yeah, we looked at that one, and the advantage of that one is got a line of sight to Earth, but the problem with it is even deeper, almost twice as deep as the Marius Hills pit. And that's one of the, we want to minimize our the difficulty in getting down to the pit.
Yeah, but it's close to Apollo. It's about 320 kilometers from the Apollo site. Anyhow, good. Thank you so much, Sam. Very nice presentation.
Thank you. Sorry about the technology glitch.
Thank you very much, Sam.
Okay.
I would like to call Vittorio Netti to turn on the camera. Hi, hello. Vittorio Netti, born in Bari, Italy, has a bachelor's and master's of architecture at Università di Venezia, master in space architecture at University of Houston, and is currently pursuing a PhD in aerospace engineering at Politecnico di Bari in Italy. He is a co-founder of 2 aerospace startups, and he is currently living in Houston and employed as a researcher at University of Houston. Yes, you may share your screen.
Okay. Can you hear me, right?
Yes, we can hear you.
Thank you, Alma, for the introduction. And can you see the screen I imagine, right?
Yes, we see it. We see it. Yes.
Okay, so my presentation seems less related to space architecture, but it actually is, and not only. It's more like we're going to talk about human in the loop testing and human system interaction, VR, XR. I work as, like Alma correctly said, at SIXA as a researcher. SIXA is, as many know, is the Sasakawa International Center of Space Architecture, and Olga like spoke before about it. But basically, in the last 2 years at SIXA, in my work as a researcher, it's a work that I started already when I was a teaching assistant here. We worked to design and implement what we call the XR testing framework. Let's go ahead and let's see what it is. This work. Okay. So extended reality. We call XR like XR stands for extended reality, and it's like a more general term that includes both virtual reality and augmented reality. It's basically it's like a term that includes a description of every technology that it's able to basically create the like a digital layer on top of our vision. So like that's as I said, it includes both the augmented reality and the virtual reality, and also what is called the mixed reality. That it's another different concept, but that's not the focus. Extended reality, but XR extended reality, it's basically what is the term that describe all this technology together. XR has a long history with the space sector. Here we see some like training, like experimental headset that I think we are here to, like in the first 2000s. So, but NASA actually developed one of the first virtual reality headset ever, like came into reality, and it's like it's a tool that is extremely important for the space sector for many reasons. So as we said, as many of the panelists like remarked today, I think like it's important to understand that it's why it's so difficult to test things for space on Earth, and for the like lack of those like special conditions that the space environment presents. That can be like a microgravity or radiation, or like extreme temperatures. So XR and virtual reality or augmented reality, all these tools, they come very handy to at least try to enhance this like this like a level of simulation, and so to make human in the loop testing on Earth, on the ground, like more similar in a certain way to what we to the conditions that we will find after like in space or on the planetary surface. So here I just listed some of the important aspect of XR for the space sector. And so the first, as I say, just right now, it's the immersivity. So like this capability to make the space nearer to Earth in a way that like make the astronaut or anyway like who experience those kind of simulations feeling more like that they are not in a ground environment, and so they feel like they feel less distance with final conditions. After we have the possibility to simulate complex tasks, this is a very important. It's usually like I noticed like investigating the different uses and scenarios of XR for the space sector that is mostly based on mixed reality. Mixed reality, it's like a it's a word that like it's a term that was invented by Microsoft to describe it's kind of like an halfway between the augmented reality and the virtual reality. So we will the difference between usually virtual reality and augmented reality is that augmented reality actually projects a digital layer on top of a semi-transparent screen like the HoloLens does, while virtual reality completely obscure our field of view and like substitute our like video input with a digital video input. The mixed reality is like mix the two things. So through usually the use of pass-through cameras on top of the virtual reality asset, it allows us like to still look at what we have around us, like the real space around us, but at the same time, it will allow to overlap a very realistic digital layer that can change the perception of the space around us. And so another big problem about usually simulation on Earth, especially when you are talking about digital simulations, is the physical interaction. And that is the reason why we invented mockups, because during the testing, we need to interact with all this hardware that has been designed. So like the physical interaction is a fundamental component of human in the loop testing. And so what makes very interesting XR technologies for the space sector is that it's way cheaper and faster than mockups. Mockups like can take months or years to be built. They cost a lot of money, and also they are difficult to iterate. So once we build a mockup and we spend so much time and so much money on the mockup, it will be difficult to have an iterative design phase in which we rebuild a new mockup with the that include like the some design derived assumption from the testing. So it's not iterative usually. The physical mockup are less iterative. Instead, like with this ability to shift immediately between digital and real, kind of, because it basically the virtual reality asset is tricking our eyes to see something that is not there. It's like there is no middle layer. We go directly from the 3D modeling to the testing. Also, another important thing is that usually it's less difficult to reproduce in human in the loop testing in normal ground conditions is the disorientation effect. So the disorientation is basically generated by an impairment between the input that we have from our senses and the equilibrium perceived by our ears and by our brain. And that was like cause the nausea also as well for the astronauts, but also for people on board on ships and in many other conditions like that. Actually, VR tricking our like eyes does exactly that. So our brain, our ears, they will perceive a certain balance that it's impaired compared to the one that the the virtual reality headset is showing us. And so that will really help us to reproduce that post-disorientation effect that the astronaut would experience, especially in the first phases of the spaceflight. Also, the important thing is that at the difference of other kind of testing, like for example, the neutral buoyancy pool or like the mock-up testing, virtual reality can be used both on ground and in space with literally no changes. So the applications of XR in space, there are many applications. The most classical are usually training and testing, but also in the last years, other applications they like become more common. Like for example, the robotic control, like teleoperations through virtual reality. Why that? Because controlling a robot through virtual reality will allow us to have the sense of depth. So it's so much easier to control a manipulator, for example, when if you are doing it through VR, because we will perceive the something that is depth, that it will not be perceived looking at the same view of the arm, but from just like a screen. That is what like usually happen, for example, with camera operations. And after like, as you can see here in this image on the right, the enhancement. So like XR, AR, VR, they can be used to enhance human capabilities. For example, giving access to so much more information in a short span of time or in a short space. Here, this is one of the first iteration, I think, of the Jarvis project. It's a NASA project about like that is still pursuing the idea of overlapping augmented reality information inside the helmets of the XM. So, I didn't talk about the most important one for us today, that is the design. This is a new concept, and that's what we are working on, because what we do at SIXA is design. So what I focus on trying to understand how XR technologies can be used for design. So not for testing, not for training, but in the design phase. For this reason, we created what is called the XR design framework. That is exactly like, now, okay, we have to describe it. And that's like the next slides are exactly trying to do that, what it is and what has been made for. So the goal of this project first is to create an XR infrastructure that will allow iterative design and testing of space hardware. This is the baseline of this project. Also, going through my investigation of like uses of this like of XR technologies in the space sector, I noticed a common thread that there is a chaos around the idea on what to do with XR and how to validate this technology for space, because there are no standards. There are no standards that allow to evaluate space hardware using XR. So, like, also this is one of the objectives of this project is to create like a standard procedure that will allow us to go from the XR testing to some design-derived assumption that can be used to like fix like certain design choices that are not optimal in that case. The third point is to define a multi-mission procedure testing framework based on highly immersive XR technologies. So here we are more like talking about, so because XR is an agnostic technology, it can do whatever it's programmed to do. So the question that we asked ourselves was how XR can be in order to achieve different objectives, like gravity testing and
Victoria, your sound is quite bad.
Yeah.
You need to talk closer to the microphone or directly to the microphone.
Yes.
You're asking me to talk nearer to the microphone?
Yes. Yes, please.
Sorry. Okay.
Okay. Thank you.
So the last point would be to so basically to create a framework that will allow in the future to apply, because like so the fact with the XR that is a technology that is like growing exponentially. Like every year there are new hardware, new softwares, new capabilities. So it's difficult to fix a standard procedure in the moment in which this technology is evolving so fast. So one of the objectives was exactly to create an environment in which we could implement. It's not like a ever fixed standard, but it's a standard that allow for implementation of new technologies and new capabilities with minimal changes to the procedures. So to go for a definition, the XR design framework is both a virtual and physical space. And for virtual physical space, I mean a place where a physical objects and digital object coexist. And at the same time, also a design standard, or like a design validation standard. So it's not just like a list of procedures to how to use XR for the space sector. It's also a product that is like a technology, like a piece of hardware, but also a piece of software. So let's go into detail of it and let's see how it works. So here it was like a general photo of the status of the like this is what during like a microgravity testing of the framework, of the physical part of the framework. But so how it works, and I'm talking about the procedure side. So we started from the design and the like the design process proposed in the system engineering handbook of NASA that's described the different interrelationships between the different system design processes that after they lead towards like the development of new space hardware. In this map, what we wanted, like we found, like what our point of ingress, like in this system, that was the design solution definition. That is should be an iterative loop. Actually, if you like, it's not really as iterative as it was designed for. Because first, the iterative testing, it's often limited by the resources. So, like, if for a project I have a certain budget, the iteration in the design will stop when the budget ends, and not when the product is good. And this is like it's a common thing with in project at NASA, and not only. Also, the problem is that the evaluation system here we can see evaluate is very subjective because it's based on basically on qualitative questionnaires. After there is really no evidence that connect the evaluation outcomes with the design derived assumption. So it's mostly like the people that look at the questionnaires, they come with some design derived assumption, but there is no scientific way to go from the point A to the point B in this case. After, like, of course, because it's based on mock-up testing, it's very complex. It's take a lot of time, and so like let's make it less iterative. And as well, the funny thing, it's usually that's what I said at the start, that basically the mock-up testing comes after the design. So usually once that you build the mock-up, there is no more money to continue the iteration, the design, and so the design stopped there. So in the moment in which the mockup is built, that's the hardware. There is no more. There are like there will be just very small changes after that. So we didn't want, of course, to like erase a very well-known and accepted like design iteration standard. What we did, we created like a new overloop. So basically, we run in parallel with this like design solution definition loop. So especially at the start, the system the NASA design framework can still continue to go as it is, but we will perform our XR testing on parallel. So after this will be also very helpful to confront and to understand what are the differences, if there is a system that is more efficient than another, if there are specific conditions in which one system is more efficient than another.
Excuse me, Vitario, Alma, because we have 5 more speakers.
Sorry.
Yeah,
I'll go fast for now. So
yeah,
I will not describe this. It was already planned.
Vitario, can you 1 minute finalize it? 1 minute.
Sorry?
Can you 1 minute. Can you summarize it?
Yes.
1 minute.
5 minutes. It's fine.
One. Sorry.
1 minute.
No,
Okay.
Vittorio, it's 1 minute.
Okay.
Thank you.
Sorry, I don't hear very well.
Sorry.
So the design, the framework has like multiple capabilities, as I said, both for we use like a crane for microgravity testing, and I wanted to show the capabilities, and here you can see in this video. So here, for example, you can see how using the framework in this case on a lunar simulation, we have on the left side, on the right side, the view of the tester, of the user, and on the left we see the real user performing the action overlapped to his environment from multiple points of view, possibly. So that allows a level of interaction and that was never allowed before without the needs to build a high fidelity mockup. Sorry, I go. About the development, these were like the 3 stages. So today we completed the project, like we completed the construction. And as this is the hardware that you use, these are the tracker. The tracker, we use them to bind the digital object with the physical object. As you can see here, there is one of the tracker mounted on a PGT drill. So like when the person will hold the drill, they will see a very high fidelity digital model of the drill in the VR system. And this can be applied to basically everything: CTB boxes, MDLE drawers, or like pieces of rovers or hardware experiments.
Thank you, Vitario. Sorry.
To conclude, the next step will be the big first test campaign that is based on the Boeing project that Dr. Banova was showing before. We will continue building these mockups that are low fidelity mockups, because the purpose is exactly that we can build low fidelity mockups that are very fast to build and still use them as a high fidelity mockup. And the last, a very important step is that we will expand the uses of the framework, not only to space hardware design that we do right now, but also to mission procedural testing, and also to test the robotic operation. And I think that was it.
Thank you, Vitario. Thank you, Alma. Very good. Thank you.
Thank you very much.
If you have
questions,
I don't know if you have time for question, but.
Matu, do we have time for a question, or do we proceed?
We don't have time.
Oh, well, we love Vittorio, and we're happy that he has his green card. We want to congratulate him on that, and we'll proceed because Ken is whipping us to get moving here. Okay, good.
Yeah.
Yes,
So if you have
let's
any question, please welcome to type in the chat or Q&A for Vitario. So Vitario
Yes.
can answer by chat. Okay, go ahead, Matu.
Matu, can I announce you?
Sure.
Please do.
Yes. Well, I would just like to say before I announce you that I will be also quietly leaving after this. The session 2 is finished when you are also finished. So I wish you fun in further presentations. So Madhu Tangavelu conducts the ASTE 527 Graduate Space Concept Synthesis Studio in the Department of Astronautical Engineering within the Viterbi School of Engineering, and he teaches space architecture in the School of Architecture at the University of Southern California. He is on the faculty of International Space University based in Strasbourg, France. He is on the board of directors of the National Space Society and is vice president of NSS for India region and the North American Activities Coordinator for the Moon Village Association. Madhu, the floor is yours.
Thank you, Alma. We are all going to rush through because, as you know, we blew our schedule long ago.
Yes, yes, we did.
We're going to run through a couple of slides. I won't talk too many, and let's hope we can close up quickly. So now, thank you for the introduction, Alma. Now, what I will do is quickly go through this project, which we call Buscraft. And the idea is to look at what we can do now, not tomorrow, not day after, but what we could have done yesterday. So with that, I'll start with this. Buscraft is an idea for an evolution for a sturdy cislunar cycle to enhance permanent lunar settlement. It was presented at the ASEAN conference and the IOC and so on. You know, USC has a long history with the moon. Neil Armstrong was our alumnus, and that is his thesis. Students come to class from all over the world. This is a group from London, UCL London. So USC has a wonderful program. It is very small, very tight, and extremely selective in hardcore engineering. And we are growing our student body, but unfortunately, we also are very tight in who we recruit into the program. So the AST studio, which I conduct, is placed within this astronautical engineering program. And the focus is very simply on imagination and creativity. No holds barred. We don't care what the agency is doing, except we steal from them when we can. But in general, it is independent of agency or industry. We have good friends, and as I said, Neil Armstrong was the commander, and the pilot of Apollo 11 is a good friend of our studio. He comes there unannounced because his honorarium can sink us in a very short period of time. So you'll see people here from faculty, you'll see doctors, engineers, lawyers, cinematographers, and my own students. They come back to get a dose of creativity and invention. So this happens in the fall. In the spring, I step into my alma mater, which is the School of Architecture. And there they asked me real down-to-earth questions. Again, the students come from all over the world, including my old professor, he's still there. And we have students from, including some people who talked in our presentation today. I see Melody there. And if you look at it, a major university always has world-class students from all over the world. And I feel it's a privilege to be, doing this work between the School of Architecture and the School of Engineering. Now, architects remind me of something that is very down to earth, and that is the space community is tiny. It's a fraction of the industry base on the planet. We look upwards and outwards with questions, while most of humanity including civil architects and engineers, look downward and earthward for solutions. Now, the United Nations has put out the Sustainable Development Goals, and our architects are really interested to know if space architects do something like this, and I keep telling them every single one of these numbers are somehow or the other associated with space architecture. Most important being sustainability, because many of the things we design may not be sustainable. Now, there is economic, political, cultural, and most importantly now, environmental sustainability. How are you going to fly through all this muck and go places and come back without getting hit by orbital debris? It's a question all of us need to think about. It's also part of what we call the environmental protection arena. Now, in terms of sustainability, environmental sustainability is popping up all over the place, not only in orbit, not only in Earth orbit, but also on planet Earth. You want to look at Johan Holmström's work, and you'll see how we are messing up our planet. So that's why the architects are on my case all the time, asking, why are we going out into space when there are a lot of problems on planet Earth? I keep telling them that innovation is the key. The human mind and the human spirit has gone through so many difficult bottlenecks. I think we can do the same again with just innovation. Please take a look at our books. These are the books that we use in our classroom. Second edition is on the right, and the third edition is in the works. Our friend wrote the foreword, and Buzz Aldrin keeps telling me all the time, competition during design phase and collaboration during execution. And I want to remind you, right now, Artemis and Gateway are all pretty much in the competition during design phase. So we want your clever new ideas to make it sustainable. Take a look at our archives. I'll leave it for 15 seconds here. Take a picture and go look at the last few projects that have been posted, including the 2022 Chase 2, in which we really bring out commercial human spaceflight as the thing that can save us and drive us quickly towards permanent human presence in space. Buscraft is an idea to build up or stack the spacecraft in low Earth orbit as opposed to flying large chunks into lunar orbit. Now, all of you need to know, the work that we do at USC is current. It's not tomorrow or the day after, but what we can do right now. And right now, we are looking at Artemis and Gateway. And you know what? It's happening right now during what is peaking out to be solar maximum. So what do? In the buscraft idea, we fly spacecraft into low Earth orbit and into geostationary orbit and get data about radiation, deep space radiation. We do not have to go to the moon to get deep space radiation data, which is critical to human survival in long duration flight. Once we do that, we start to go to the next part, which is to use what we call LEO to lunar orbit cycling. And all of these things are elements that are either available, existing, certified, and commissioned, or in the process of commissioning. As I said, just a mile down the road from here is SpaceX, and they have some of the most reliable launchers ever to be on planet Earth. You're looking at Falcon 9, and I think in the next few days, you'll see Falcon Heavy roar into the skies again. And but just with these two of the Falcon series, you can fly to the moon and back. Of course, this will come online, I think, in a few days. FAA has cleared it for flight. Notice the mariners around the globe have gone out, and we hope to see the new generation of fully reusable vehicles. But we don't need this to go to the moon right now. We can make do with Falcon 9 and Falcon Heavy. What would we do in phase one? We'd fly a vehicle like the stack on the right side. It'd go into low Earth orbit. From low Earth orbit, we'd cycle through the Van Allen belts for as long as we like, and then go to the geostationary orbit. And with that, we can study a lot about deep space radiation. In phase two, we go to the right side and build the buscraft stack in low Earth orbit, and we go from low Earth orbit to low lunar orbit and back. This is what a notional trajectory would look like. We are still struggling with it, but I know there are things. We have people like Adamo. I think Ken will bring him here, who will be looking at these kinds of trajectories. The main idea here is not to put people into lunar orbit very early on when there is very little help for them to bring them back in case of anomaly. Remember, it is solar cycle 25 maximum coming up exactly during the time we want to fly humans into lunar orbit and back. So what do? We have a system where you have a cycler that goes around the moon and back every 2 weeks. So during those 2 weeks, you'll have intercepts of the moon every week. And as they fly back through the Earth, we have a high energy rendezvous, change out things. We have put plants and animals there before humans so that we can take a look at how they behave before we put people in orbit. And in case, God forbid, there is a CME or some kind of a flare that affects, you can quickly bring our crew down. How do you handle the propulsion requirements? TEI can be done using modular cluster propulsion. Again, we are not going to throw stages into heliocentric orbits or lunar orbits and crashing stages into the moon. We want to have lunar orbit. And the secret to that happened last year, late last year. It's called the inflatable atmospheric accelerator. We've known that we can do aero brakes for a long time, and we want to introduce the aero brake, the atmospheric accelerator into the system to bring back the modular clusters and refurbish and reuse them for flight. We will not be using any more expendable vehicles. We are going to go through these because these are very well studied problems. What is the maximum benefit of buscraft? If we do things in low orbit and integrate the stack in low orbit, many nations of the world can be part of this program. And there are many launch vehicles and many launch sites from where we can fly. So there's a truly an international endeavor. Of course, the important thing is to know that the lunar orbit, the plane of the moon, is very close to it. Equatorial plane, not very interesting for the International Space Station. So we have to fly in what we call the free return trajectory. NASA wants to go out of the free return trajectory and go to the polar regions, which we will do at some point in time, but not while we are testing a new set of vehicles. We want to go fly in the equatorial plane and make use of the free return trajectory, exactly like Apollo did. Now, as you know, Orion, the first flight of Artemis 1 was on that plane with the free return trajectory. Second one too will fly. Third one is the problem. The moment you leave the lunar plane, you are asking for a lot of energy to get out and get back in. We also think that using optical links is the way to go, because optical communication serves as the backbone for planet Earth right now. We are going to use laser comm, and it's already happening here at SpaceX as well as other areas, and we hope to use that as the carrot to bring people together in the Artemis Accords, which is struggling with about 20 or 23 signatories. We want to raise it to 60 or 70 in a matter of a year. So, what are the recommendations? First of all, we need to tell a really nice story. You cannot go to a dark place called the South Polar region of the moon and hope to have beautiful visuals of people working in pitch black, extremely cold environments. We want to use existing assets, and we want to get deep space radiation dragon out of the question even before we go to the moon. So there are many things that we need to do, but we've not gotten there, like PRAM, we're going to do that, but we were studying all these things at USC. In conclusion, I would recommend that we return to the moon now. Don't wait for tomorrow. Don't wait for next month, next year, and next Christmas, and so on. Many conferences and meetings coming up. I hope we'll see you there, or you will see us there. And again, competition during design phase, collaboration during execution. And we did not use Buzz Aldrin, but if you look at his T-shirt, he'll tell you that we want to go to Mars. But if you ask him a little question, little detail, he'll tell you we are not going to Mars without stepping on the moon and really studying the operational aspects of lunar surface activities. Please go on here, take a look. And that's just my presentation. Thank you. How long did we do? Very good. Okay. So you are the good. Next session. Okay, so guys, hold on tight. I know we are losing folks. Okay, we are directly going to some spectacular, I wouldn't call them newcomers, but they are very effective players in the space architecture community, and we wholly welcome them to join the SATC and present their works. But I want to take the first digs at some of these wonderful people who are doing very special things that would be very useful for us in this very youthful endeavor. But first would be Kaya, who is dialing in from Australia. Where are you in Australia, Kaya? Tell me again. You're not at RMIT, but you're at Deakin University. Where?
Yeah, still Melbourne and Geelong. Yeah.
Oh, great. Okay, and it's a beautiful day there. Or wait a minute, what's the time?
It's 9:16 a.m. It's cloudy day, and I think it's half raining. So, but it's okay.
You're looking good, Kaya. Kaya is a lecturer in industrial systems, right? In design, and she has some very interesting angles on all of these things that we do in space architecture. She wants to bring space architecture down to earth, and she's already been discussing this with our own folks here in Southern California at the Science Museum and so on. Welcome, Kaya. Please go on. Let's do this in 10 minutes flat.
Okay, I'll try my best. Thank you, everyone, for inviting me. I wish to begin by acknowledging the Bunurong people of the Kulin Nation, the traditional custodians of the lands, waterways and airways on which I'm actually presenting here in Naarm, in Melbourne, Australia. I also paid my respects to elders past, present and emerging of all the country on which we do our business today. So addressing individual differences and cultural diversity becomes crucial as human space exploration advances. Our initiative emphasizes the importance of personalized, meaningful experiences for astronauts on long-duration isolated missions and individuals living in socially isolated environments on Earth. So as you're familiar with, NASA identifies 5 hazards of human spaceflight. And the project that we are proposing aims to develop heritage-based immersive digital solutions that enhance the well-being of astronauts during extended space missions. So the focus will be on enriching everyday activities such as eating through heritage-inspired multi-sensory extended reality experiences. So those will be supported by artificial intelligence and machine learning. And this experience will be developed and utilized to monitor the well-being of astronauts, such as their emotional states, in obviously in objective way. So to achieve this goal, novel and unique XR experiences will be designed and developed in collaboration with museums and indigenous knowledge holders. So furthermore, as we design for space, we also need to spin off technologies. So these immersive eating experiences can help people in isolated environments on Earth. For example, if we think of people in prisons, in elderly or similar experiences are already being developed for older adults, as you can see here. XR eating experiences will be tested with culturally diverse museum visitors, also in analog missions, and later we hope to develop solutions for future long-duration space missions. But first, it's really important to test using citizen science approach within museum settings to boost audience engagement and to get a very diverse data from people coming to the museums. The increasing diversity in space exploration necessitates a deeper understanding of cultural context and diverse backgrounds when designing for well-being solutions for astronauts. So for instance, Artemis program aims to land the first woman and the first person of color on the moon. And on the other side, Australia, one of the first partner countries to sign the Artemis Accords, is also preparing to send its first female astronauts into space, showcasing the country's commitment to contributing to global space exploration efforts. So the National Indigenous Space Academy is another initiative highlighting the importance of diversity and inclusion by embracing a holistic perspective on a sense of place and a unique Australian perspective. So just recently, in March 2023, NASA Administrator Bill Nelson announced this program. So astronauts report challenges such as loneliness, boredom, discomfort, sensory deprivation, and diminished cognitive performance and stresses while in orbit. Excuse me. You can read about this in astronauts' biographies by Cristoforetti and others. Then if we think about emerging research from analog missions, they also suggest that nature-based XR experiences can improve mood in isolated, confined, and extreme environments, or ICE, as we call them, particularly when they are tailored to personal preferences. Then also there is a growing evidence that visiting museums, galleries, and historic environments can have positive psychological effects that can be explored further for use in human spaceflight. As pointed out by Dwayne Hampshire, indigenous knowledges provide solutions to sustainable living, adapting to changing environments and maximizing the health of the land on a continental scale. So the rationale for this project lies in the potential of sand-enhanced XR experiences to address challenges faced by astronauts. So the sense of smell plays a crucial role in our everyday lives, significantly influencing emotions, memories, and well-being. So incorporating into XR experiences, this can enhance presence and immersion, resulting in more realistic and engaging experiences. So researchers have previously emphasized the importance of enabling personalization to allow individuals to enjoy their own preferences for familiar and pleasant night-based plant aromas. And Madhu has been working on this as well, as I believe. And artist Carrie Peterson has also explored scents for space travelers, as well as for refugees and immigrants. So her project is called Homesickness Kit, and you can find more about this on her website. So these approaches highlight the need for tailored and user-centered perspectives when designing scent-enhanced XR experiences for diverse heritage groups. Integrating scent elements into XR experiences requires innovative approaches and technologies. Immersive exhibitions such as Van Gogh Alive use natural scents to enhance XR museum experiences. And there are various researchers who are also looking at how multisensory VR can support astronauts during those long duration missions, incorporating scents in nature-based experiences. Speaking of food, food provides a natural environment for exploring cultural heritage without provoking conflicts due to diverse backgrounds. Inherently social in nature, mealtimes offer opportunities for sharing experiences and fostering connections. As a result, meal environments can be utilized to facilitate relationships between crew members or with family and friends on Earth, using food and eating experiences and cultural activity to enhance social interaction and elevate feelings of isolation. So cultural heritage is initially linked to identity, and the sense of smell has the power to evoke memories and strengthen one's sense of identity. So as partly Slovenian, I wanted to show, for example, NASA astronaut who is also Slovenian and Indian descent took the traditional Slovenian Kranjski sausage to the ISS, which is quite a known story in our country. So by emphasizing heritage, diversity, inclusion, and the notion that space is a domain for all, this project recognizes the importance of cultural context in designing immersive experiences. So on the left, you can see our colleague Julia testing such a dining experience in Japan. The experience by a well-known team lab incorporates seasonality as well as culture during shared eating. So the significance and innovativeness of this research proposal stem from its interdisciplinary approach. And this collaborative efforts highlights the importance of diversity and inclusion within the space sector. So drawing upon underutilized resources like indigenous knowledges, as well as cultural and psychological benefits of museums. So the project addresses 5 objectives to create personalized heritage-based XR during experiences for astronaut, dining experiences for astronauts. So first, we want to understand meaningful XR elements suitable for future diverse crew of astronauts. Then develop an AI-based model to monitor smell and emotional responses using the developed meaningful XR elements that use artificial intelligence as well. So XR content and visibility of attachments for enhancing the sense of presence will then be developed, and this will be tested in space analogs in a larger cultural context, such as in museums, by using a citizen science approach. To conclude, the main aim of the project is to develop technological and content solutions for stimulating multisensory extended reality intervention during food and meal experiences in isolated, non-stimulating environment. So this project has received its first seed funding from our university, and I would also like to thank our core researchers for their passion and expertise. And also, we have received 2 Deakin Coventry PhD co-tutor scholarships. So perhaps if anyone knows anyone interested, we are currently looking for 2 positions. We got 2 open positions, one for VR designer and another for AI developer to join our team, both in Australia and in the UK, and then the students will swap. Also, a short invite to our, we would be part of an event here at the Science Works in one of the museums in Melbourne as part of Melbourne Design Week. So if you want to join online, Sustainable Design Beyond Earth, it's our session during the future forums. So thank you so much for your time, and I hope it was quick enough.
Oh, very nice, Kaya. Thank you very much. So many questions about XR for you and Vittorio, but I'll email those to you, and we'll have a good discussion, because there is so much of psychology that we need to look into, delve into. But thank you very much. We are not going to be taking questions, but please shoot questions on chat, and I'm sure Kaya will respond. With that, we're going to my friend Samer, right? Samer is an unusually gifted designer and architect, and he's coming to us, I believe, hooking up from the wonderful, famous place called Alexandria. And are you there, Samir?
Yes, can you hear me now?
Oh, very well. Good to see
Okay,
you, my friend. Take it ahead. Again, we want to rush through 10 minutes and on and off, because the library is going to kick us out.
Okay,
Okay, go for
I'll
it.
try to do that. Thank you so much for having me today, guys. And just let me share my screen to start right away. So my presentation today, I'll just skip the technical part that have already been presented so much in the previous presentation. So just let me dig it to the different part, or the core unique part. So my presentation today is called Rationalizing Nature. I do believe in natural-based solutions in space exploration and designing space habitats. So, I'm sorry, is it moving? Okay, so just to summarize, or to start with my manifesto, I do believe in the quote of Le Corbusier, the father of the modern architecture, when he said that, you know, it is always life that is right and the architect who is wrong. So he implied that working in alignment with nature is the core essence of the modern architecture, and that resulted after like 5,000 or 6,000 years of sharing, accumulation of experiences, until we reach that conclusion. So the first thing is digging deep. This is my own manifesto in 3 steps: digging deep in the old knowledge and science accumulated through thousands and maybe millions of years to capture hidden values and intangible strengths of our nature-based systems. And the step 2 is developing those values and strengths using cutting-edge technologies to create a state-of-art design that carries the mentorship acquired from nature, not in its shape or form, but in its experience and core science. And the third phase, and the last one, is documenting and publishing those experiments to deliver them to the future generations. And one of those manifestations are the presentation of that I'll be delivering today, in addition to papers, exhibitions, conferences, whatever I can just send my message to the future. So the presentation today will start with a project that I've been awarded just a couple of months ago, last December, in an international space competition called Jacques Régéry competition in Paris. And I was fortunate enough to be granted the grand prize. And starting from the next year, I'll be assigned as a judge in this same international competition after 7 years of winning with them. So what is the story of Mars Reefs? Well, the new thing is here that even if it started as a fun project, but I try to use the AI, including ChatGPT, image text generators, just to stimulate and start brainstorming, unlocking synergies to understand how can I approach a space habitat with a new vision. Just to mention that the colonies that I'll be presenting is classified according to anthropologists as the third phase colonization, which means that it will be a permanent residence and it will be using the third class architecture, which is the ISRU, or in situ resource utilization, in collaboration with the first class, maybe on the second class. So it is a hybrid class. So after asking ChatGPT, can coral reefs offer us a solution, as it is considered as one of the most durable and sustainable form of colonies that carries various life forms? And really the answer was for me satisfying, especially point number 4 and point number 5, when it referred to that coral reefs are essential ecosystems that provide habitats for a variety of marine life. Architects can incorporate sustainable design principles out of them into their compositions. They resisted all kind of existential risks that could be really imagined, and they might stay for like hundreds of years and can host all of those various life forms with a minimal impact on nature. So the second point, which the function, the coral reefs also provide a range of functions: protection from storms, erosions, as well as opportunities for creations and tourism. So that was the first inspiration. And then switching to the text image generators, which are try to understand the classification of those kind of coral reefs until I reached my destination, which is the brain coral reef. And here comes the way of rationalizing nature. Nature is not chaotic, but it is random a little bit. So randomness is okay. Randomness, you can put rules and theories, and you can take out, you can reproduce nature of understanding its algorithms. So switching again to ChatGPT and asking them, can I really rationalize nature? And the interesting answer came in branching, in understanding how the branching, the interconnectedness, and the repetition of elements can work out. And according to my experience and some of my professor colleagues that are specializing in shape grammars, and I switch to them, asking them for guidance, and we start understanding more about shape grammar. And I found that putting some rules and some vocabulary in collaboration with each other I can really reproduce nature. And the rules came in the scale and the proportion and the orientation. Switching again, and this is maybe the major slide, that I try to rationalize nature, to take out vocabulary out of them and to set out rules to reproduce them, and to reproduce a durable and sustainable system that can maneuver all geographical and harsh environments, and at the same time provide me with an ISRU solution, just like the coral reef as considered as an ISRU colony from a solution that Mother Nature offered us. And it is just about in front of our eyes thousands of years ago, but we didn't really appreciate. So by setting out those five first vocabulary and then extending them to another 10 vocabulary with their different rules, I started providing or designing the colony with a consistency to make it easier for the class one architecture to be inserted inside this ISRU colony. Switching again to the text image generators AI to understand the solid and void relationship between both of them. And later on, that was the birth of the project Mars Reefs. So Also, again, the quality of the interior spaces is another important part, the humane part. We are not just providing storage for human beings or Homo sapiens. We have to provide them with a human experience, one that can resist the different psychological problems that astronauts might face for a long-term durations. And from here, I start understanding that I have to allocate each part of the architecture program, the architecture requirements, and in a unique experience as well. You can see from this slide on the right that this is a hybrid class 1 architecture, the pressurized modules that is inserted inside a high wrap of ISRU 3D printed colony, just to provide it with enough protection against radiation and against micrometeorites and so on. And at the same time, it could be also providing shelter for the pressurized rovers just beneath the main shelter, and to decrease a little bit the sandstorms and to decrease many of the hazards that can affect the electronic parts of those rovers. With a very high and very long rods that will be oscillating and vibrating with a piezoelectric energy, enough to start powering the colony with a passive long-term solution in case that the solar panels could be covered with the Martian regolith according to the long-term storms of the Martian environment. So trying to find solutions for the future. Switching again to the AI, and I started searching for solutions for the infinite connections of those modules. And I found, of course, prompting and trying to insert the right prompts to the AI. I found my solution in the AC ducts. It is the most likely and similar solution to the pressurized modules of class 1 architecture. So I tried and I prompted, and it resulted in maybe more than 1,200 piece of image that I've just reduced to those 2 images. And I started designing the interconnections and the branching system of the pressurized modules that will be housed inside it. And then later on, I housed all of this colony just above a Martian lava cave. So we have like 2 parts of the colony, one above the surface, which is the ISRU 3D printed part, and the another one which will be dedicated only for the farming solutions inside the Martian lava cave. And this particular part was awarded in 2017 in Mars City Design, the first award energy inflatable energy category for producing a farm unit or for food production unit, an inflatable lightweight capsule that will be equipped with all nutrients and ingredients, and it will be operating with a zero waste and zero energy requirements. So it will be oscillating and it will be producing its own energy, and at the same time those contoured lines is the LED lighting system that will be providing all of the farm, the plants inside it with enough light to overcome the photosynthesis deprivation due to the solar, due to the storm, Martian storms that will be depriving the plants from enough sun rays. So trying to insert it just above the skylights of the collapsed openings of the Martian lava cave. And this will be most of the process in 4 steps, detecting the appropriate skylight and just trying to insert the infrastructure of the pressurized pods before reinforcing the outer surface, and then covering it with regolith, and then just leaving the openings for the ecopods or the hydroponics pods to pop up and start gaining the sun rays for the photosynthesis. And this is a double layered, by the way, inflatable with an aerogel inserted between them just to protect also the plants from the cosmic radiations or the solar flare that might result on the Martian surface. It will be inserted strategically in a circular formation just to ensure that it will be provided equally to the colonists or to the astronauts around surrounding, and there will be like 2 main farmlands and another main farmland beneath the surface in the Martian lava cave. This is the allocation of the site, and as you can find here that there is a diversity. I try to diversify between the powering systems. So the main or the first power system will be the solar-based satellites in the low Mars orbit, but the main solar power will be the kilo power unit that will be allocated remotely a little bit, just in case any emergency that might occur. And of course, the one that I have mentioned earlier, which is the oscillating piezoelectric rods that will be also generating energy in case that there is a sun deprivation and the solar panels might not be functioning. Later on, surface solar panels could also be added to the whole system. It is very important and crucial to diversify between power because power is a critical decision. Without power, the colonists will not be able to live. Power is important for the oxygen generation, for the water generation, for powering the farms, for keeping the temperature, for even operating the whole system. So it is very important just not to put all of the egg in one basket. That was not the only solution. Before it, there is another awarded project called the Iris. And Iris in the Greek mythology is the personification of the messenger of gods. And that was the first infrastructure that I do believe it will be connecting Moon, Earth, and Mars together. So it is working in alignment with the Greek mythologies. But also it has another aspect, which is the iris of the eye. And that is another biomimicry or another natural-based solution. So this lunar elevator that I'm presenting now is not only an infrastructure to connect Moon, Mars, and Earth, it will also be acting as a deep space telescope, as a scientific facility in addition to its industrial facility. It will be operating majorly on helium-3 components, and that will be the main resource that will be paying for the whole party. The investments in shipping the helium-3 back to Earth and maybe even to Mars, it will be the main reason to find enough funding and investments in such a project. So that is the subsurface, or this is the above surface. It has another part which is the underground or under the lunar surface in another Mars Tranquillitatis pit crater. So that will be capping the pit crater just to provide it with shelter and to start another life. And by the way, the combination of those projects just recently, 3 days ago, it was promoted as a winner in the Promo Moon Initiative in phase 1, and I'm developing it right now for the final stage. So that will be the lunar lava cave also, and it is called the lunar oasis. And the lunar oasis is a self-sustaining also. It's a zero energy, zero waste circular economy, circular closed loop system, and it is based on many driving force. The first one, the first inspiration with the oasis, the first form of life. The second one with the circular geometry or the circular formation, which is hardwired in our brain with the sense of tribe, family. Even when we use the notion in our words, when we say circle of trust, circle of friends, circle of family. The third is driving force with the anthropization, like terracing mountains for farmland, which was converted by the parametric design into contours for the ease of construction and maintenance. And the fourth driving force with the ant colonies, also another super sophisticated form of habitats offered by nature. And it can also resist all kinds of existential risks for those little fellas. The fifth and the final driving force is something also which is considered to be something inspired from our ancient civilizations. It's the sacred geometry, which is known as the cosmogenesis geometry or the cosmogenetic architecture. So all of those driving forces resulted in the form finding of the lunar oasis project, which will be divided into 8 sectors and 8 independent, decentralized life support system, just in case of one of the system might face a failure or something, for God forbid. So all of the system will be carrying each other as a one huge network, but with a decentralized sectors. Switching from space technology, we have learned a lot from NASA spin-off technologies. We have to start designing Earth habitats with the same mindset. And for me, I'm not 100% space architect. I also work for terrestrial architecture. So I had the responsibility to just convey this knowledge into our Earth architecture and start designing Earth habitats with a fresh and new mindset, the mindset of a space architect, but working for Earth. So those are some of the projects. I don't have the privilege of time to present all of them, but I'll just refer to quick samples out of them. So one of those samples is the Square project, the one that I have highlighted with the red color. The Square project, it is a very minimalistic and very small house or a habitat that is considered to be a zero energy, it will be producing its own food. So it contains its own food production unit. Also, it will be collecting water from the rainwater management system and from the fog and dew also water. It is a zero energy, it's a food production, it is a water securing. So it is a decentralized form of housing that we should design. It is an off-grid and it should be designed as an off-grid. So you can build it in anywhere without the connection to any governmental grid, either it is water or infrastructure like electricity or whatever. That is part of the research that has been 50 design criteria that were derived in the last 10 years from my for work and research just to design this simple white box. So as simple as it might seem, but it carries the most sophisticated research work from the last 10 years. And this is the site. This is what is considered to be a harsh environment, but harsh environment on earth, extreme poverty, extreme and contagious and sickness that is spreading out and no resources. And so this is a harsh environment. We are designing for space, but we have to consider our current society and communities on earth. And that was the mind of the space architect. That is the International Space Life Support System. That is the same diagram that was simplified to redesign that habitat on Earth. So this is the part of the formation process of the food production unit. It will be a piggen tower, which is a very ancient practice in Middle East here. And it is considered to be an economic activity, and at the same time, securing some of the proteins for the residents. But also there are hydroponics units with the same time, and it is also containing a stairs or a vertical circulation with a rainwater collection unit and a wind catcher. And after laying out the main conceptual design, I had to test that design just in order to make sure that it will be functioning, at least according to digital simulations, as it is intended to be. And referring also to many of the references, I do, by the way, define myself as a scientist and an architect. I use science for producing architecture, and after making this architecture, I turn it again into science through papers and conferences. So it's a cycle, it's a closed cycle from science to architecture, and again from architecture to science. Most of those simulations was done during the last year, even after this project was awarded the first prize, but the work in progress is never ended. My client is not a specific client, but it's dedicated for humanity, for my community, from society, from next generations. This is the main calculation and offering several solutions, one of the facades and the other on the roof, in case that it will be a multi-floor building. Also, it is designed with different scenarios. The humane part, the delightful part, the Venestusis, according to Vitruvius, which is the art, also inspired from the local pop art of this place, and simplifying that art pieces into just 4 primary colors that was used in the lightscape study, just to give them an everyday celebration to embrace and to elevate their psychological part as a human beings. And designing it with extreme adaptability and flexibility, just to ensure that it will be facing various urban scenarios and successfully it can deliver urban solutions. And this is not a solid block, it is a porous mess that can embrace biodiversity, embrace wind, and embrace the nature, and offering inside its vertical courtyard a frame of nature. So as if you are capturing the views of nature also inside your habitat or house. This is a depictions of the solutions in different urban scenarios, one of the in the farmland and another. And even after the project has been awarded, many simulations, and again, the research work is working on. That was not the only solution. Before it preceded House of Suhaimi, which is also considered to be a zero energy, zero waste, decentralizing housing prototype that is designed for 3 different generations to live inside the same mess. You can find here upward the farm. It is not a hydroponic system, rather it is a complete roof farm system with solar panels that can secure from about 10 to 10.5 kilowatt of electrical power per day for the residents, and having passive solutions for the AC system and everything you can imagine. This is another also awarded project for Arizona environment. And this is another one for the German environment in a city called Cottbus. It was designed for Cottbus, and it it was designed to face the pandemic or the pathogenic explosion that happened in 2020. So it is also using a lot of technology. And by the way, this is not glass. This is called aluminum oxynitride. It is considered to be transparent aluminum or transparent metal, one of the top-notch technology that have occurred till now. And it can also resist all kind of intrusions or impacts and it's considered to be a structure system, but it is as well transparent. And learning from space architecture a very important lesson. So each space or each room is a complete closed pod, and you can transport even your rooms to capture the view that you'd like to have. And learning also from the hygienic principles, designing the WC system with a spherical, just to gather all microbial life form at its end to make it easier for the disinfection and the purification of such a space with a disinfectant lobby. And of course, a robotic system that will be just yeah, 2 slides and I'll just finish. I'm sorry if I took a little bit longer. So it came to an end, fortunately. So thank you. I'm sorry that if I've just talking a little bit quickly, I try to follow the time schedule.
Delightful. I can watch this for hour on end, Samir, because you're so very creative. But we got to go on. And if you have questions for Samir, please post them on chat, and Samir, you can respond.
You can reach me anytime.
It's a delight to see your work. Now, our presentation is from none other than our grad student who just, you graduated this year.
In like 3 weeks.
3 weeks. And so let me introduce to you none other than Claire Stavlinson. Claire has started to work for Axiom, and she used to work at JPL before. And we are good to see that she's graduating and heading on to professional work. Welcome, Claire.
Thank you. Here, I can grab that. Will you give me permission to share?
Yeah. You can share, yes. Go ahead.
I don't have a button to share.
If you go to share
screen, they should have a.
There's no button.
I thought sorry. I thought you were already. Oh, because you are in person. I thought you were going to. Okay, sorry. Yeah, accept it. Now it should okay. It should be okay.
Beautiful.
Okay, we got you.
All right. Hello. As Maggie said, I'm Claire. I'm currently a master's student at USC, just finishing up, going to graduate in a couple weeks. I was in his class in the fall where I came up with this initial concept. So this is RALIS, the robotic assembly of lunar inflatable and erectable structures. So first, problem and concept solution overview. For this early lunar settlement, my main objectives are the where, why, when, and how. And so looking at the research and what's been done before, decided that the Mare Tranquilliartis would be an ideal starting location point for this. Why, and then can also go along with the Artemis 3 timeline. So there will be a lunar habitat for that. When and also the where is so that we can have that free return with the SLS missions and staying in that system and timeline, and then either in conjunction with their mission on SLS or separately with Starship. And so the problem I'm hoping to address with this concept is that there's a lot of concepts out there for lunar habitat, as we've seen today. A lot of them have very long, extended timelines and are very complicated and involve a lot of R&D, such as the 3D printing that involves sintering and having to go through the regolith and the in situ resource utilization, where I'm hoping to have a concept that kind of optimizes work that's already been done, both here on Earth and in the lunar sphere, so that it's the most efficient way possible to get us back to the moon now. And so some background, as I mentioned, the 3D printing, using the regolith as building material, it involves a lot of complicated machinery and is very time intensive and probably better in the later phases of lunar settlement instead of trying to use it as our first approach. And then also crude construction is very costly, higher risk, and you need a lot more redundancy if you're sending people right away. And so also a little more background on different types of structures. You can either do pre-integrated, so sending up something that's already completely assembled, have the erectable and deployable, where you send it up in either a kit or deflated and packaged, and then either spring it out or erect it there, or the ISRU based, which I mentioned, the 3D printing and using the resources on the moon to build completely new structures. And so the concept that I'm proposing is a hybrid approach that we use more of that class 2. So it's quick, it's easy. You have a kit that you're using and then not having crude construction, but instead using autonomous robots to get it done quickly before humans even have to go to the moon. And so first of all, the autonomous robots would excavate this landing site, and then they would be able to assemble the kit themselves. And then that would be your outer structure, and then have a deployable inner structure with airlocks for human habitability. And so a little step-by-step process. First, you have a lander with some of your autonomous construction robots. They'd be able to construct a pad using like a lander kit that they bring with. And then once you have a pad set, you can have a larger lander with your kit for your actual deployable and erectable habitat. And so then your robots are able to prepare the site using their excavation tools and then assemble the structure themselves. And so this is what the structure would look like as an initial concept. You have that outer structure, which is your erectable. There's companies that do this right now, such as the sprung structure. And you can have an inner, outer erectable. So you have a Whipple-like action for MMOD protection. And then your deployable inner habitat, which can be deployed using those autonomous robots as well. And so some of the key features on this, as I mentioned, the Mayor of Tranquilar's landing site, you have your autonomous site prep, your erectable structure, your inner inflatable habitat, and then your airlock. And so for the landing site, the equatorial Mayor regions are heritage. There's been astronauts there. We have direct communication, and then it's also relatively flat, smoother terrain for your robots to easily work. And then you have the autonomous site prep. This is being done terrestrially already with these autonomous construction robots being able to erect structures here on Earth. And so doing this on the moon, you'd be able to do it with little human intervention and have your structure already set up before even arriving. And these are just some examples of the lunar excavation tools. And then your erectable sprung structure, as I mentioned, you can just send up a kit with all the parts, erectable, and then you can also have your thermal shielding, radiation shielding, MMOD protection, all built into that. There's no foundation, which means less actual construction digging, just very easily erectable. And then you can have modularity on this as well if you want to expand. And then the components of this is you have your rapid construction. It's quick and easy. Design flexibility, just that outer structure you can design for whatever your purposes are. Performance and durability. These have been used on Earth. No R&D is necessary as much as using the lunar resources, and then lower overall cost because of that as well. And then your inflatable inner habitat, there's been some concepts for lunar and orbital use already. And then this is just the quickest and easiest way to produce pressurized habitat. And then your autonomous robots can deploy it and verify that and have everything all set up and ready by the time humans arrive. And then you have the airlocks. This is a NASA concept that would be easily expandable and packaged for flight, and then just expanded with the use of the autonomous robots. So then, summary of all this, you send your robots, they build the landing pad, they're able to excavate, dust removal, and all the site preparation, and then they'll be able to assemble the sprung structure easily on their own, and then deploy the inflatable inside. And so the key points, your autonomous construction plus your erectable inflatable kits means a quicker and easier way to get to the moon now, instead of having to do a lot of excess R&D for projects that may take decades. And then the next steps for this are just making account ops, cost estimates, and then more detailed design on the actual erectable and inflatable structures. That's it. Thank you all. Try to get through that fast.
One second. Oh, thank you, Claire.
Now that they take a picture,
Oh,
Okay.
Oh, my God. He gets an award. All right.
Thanks.
show it to.
Oh, what a picture. All right. Yeah, I didn't know this was happening, but Ken is super efficient. What do you do?
Don't stand in the light. Yeah. One more. Very good. Thank you.
Thank you. Where do you want this one?
Oh, good. Okay, guess what? We are in reaching the end of the marathon here, and my wonderful other student is online, I know. So, can you?
Yeah.
Carla? Is Carla, are you there? Oh, there she is. Good. Howdy, Carla. You're going to be the show ender. I'll have a few slides to close up, but so glad to see you. Yeah, please introduce yourself, because I know that you are a Lockheed Martin employee, but what are the other exciting things you do before you screen images?
Well, I was a Lockheed Martin, but now I'm in Raytheon. So Raytheon Technologies.
I remember that. Okay.
But I would consider myself an entrepreneur and a culinary tourist. I am I took Madhu's class. I have a master's degree in system architecting and engineering from USC, and a master's degree in electrical engineering as well.
A whole bunch of awards. I've been looking at them, but go for it, Carl.
So I will try to make this quick since this is the last presentation here, and let me share my screen.
Carla is going to get us going on the enzymes in our tummy for food, because she's into culinary stuff. Okay, go for it. And Carla presented at the IAC, followed by a few other presentations at the AIAA, and now here she is.
I don't know why I can't share. Somehow.
Ken,
Oh, Carla, yeah, I kind of should be on the list. Do you see the green button? Yeah, Carla, you should have a green button at the bottom. The menu.
Oh, I gotta quit and reopen.
Did you see a green button in the menu?
Yeah, but somehow I have to reopen my Zoom.
Take your time.
Okay. Let me leave just for a second.
The library
close officially at 6.
Oh.
We have the room supposed to 5:30. If you really, really want to run a little bit over, I think they will allow us.
No, we can close at 5.
But it's better before 5:30.
Close it. Let's
I
see,
can
close it.
see it. I can see it.
Yeah.
I'm waiting to have like put the
What-
slides
what
up there.
direction?
And then
Okay.
I also think that like EVA suit mobility is
We're good.
bad. Like it's not doing.
Yeah.
Yeah, I guess.
Yeah, I think it's just.
Carla, I got it.
Exactly. Yeah, I'm sorry.
You landing in my strategy already, yeah.
Okay,
Seems to be working. Go ahead.
sounds good. All right, can you see my screen? Is that
Yes, yes.
it show? Okay. Think I'm, okay.
Looking good.
Yeah, so as Matthew mentioned, this is the part of the Chase project. I was in the 2021 class, and so my concept is creating human experience through food, or chef in space. All right. So just a quick background. I mean, it is part of promoting the Chase, and that plan proposes an early transition of the ISS operations from NASA spaceflight projects to a university consortium and private sector. So the objective of the Chef in Space project as part of that is to serve gourmet food and provide the space travelers with an exceptional dining experience. It also hopes to address the challenges of creating a more palatable meal and providing nutritious and tasty food that would cater to the individual's caloric need. And I'm not going to go through the space food history, but I wanted to point out that, you know, NASA has constantly found ways to improve the space food system, and using based on the constraints that they have. But as of today, all of these are prepackaged and prepared on Earth, and there's still no cooking in space. Here's a deep space food challenge that NASA and the CSA launched, and the focus that they had was on manufactured foods, bioculture, and plant growth. And what Chef in Space hope to contribute here is the technology to enable cooking in space. Now, there are all these new technologies that exist today. We have the hydroponic technology, robot chef, telerobot system, Astrobee, and additive manufacturing, to name a few. And all these technologies integrated together would create this automated space kitchen. So here, there are so many space-themed restaurants that offer an out-of-this-world experience. And recently, Disney just opened up a space dining experience in Epcot. I've never been there, but I've seen a lot of pictures, and it gives people the visual environment of being in space, but not necessarily the microgravity dining experience, which can only be achieved in space. But it's only a matter of time when all these space hotels and ISS becomes a hotel, in which dining areas will be retrofitted into these. The Chef in Space concept is then to provide the food experience and technology to build the future of customized and nutritious meals in an automated way. And this concept can be applied in short and long journeys anywhere on Earth or in space. So it is using the pressure cooking concept. It has been used for centuries, and it's still a popular method of cooking as of today. The technology has definitely improved over the years with mechanisms to prevent devices from accumulating too much pressure and exploding. So it is definitely much safer now than decades ago. But why the pressure cooking concept? Well, the principle of ideal gas law would still work in these space stations and space hotels because the cabin pressure is the same as the sea level pressure on Earth. Additionally, not only does it shorten cooking time, it maintains the quality and integrity of the food. So I'm proposing that the pressure cooking technology be introduced in space just to aid in that gourmet food creation. And this is my chef concept architecture. There's the module, the kitchen capsule, the solar arrays, and the power module. And they're dedicated to the robotic kitchen. This is the inside view of the kitchen module in which you would see familiar equipment you'd find in a traditional kitchen retrofitted for space use. So there's the environmental control module, the command and control, which is really the brain of the kitchen module, orchestrating the dish preparation process. There's your pantry, the prep station. There's you always have to clean after you prep. So there's the cleaning station. And then the Astrobi is where the Astrobi food attendants would go. And the pressure cooker module, which houses the pressure cooking technology. And lastly, there's the robot arm module, and each of the robot arm performs specific tasks. And this is just an example of how it may sequentially perform the task. And then the Astrobi food attendant station, on the left is just, and gives you an idea of the size relative to a human adult. And so here's the Astrobi delivering the food, Astrobi with a robot arm placing the food in it. And here is the Astrobi charging. This is just the functional flow of the chef in space adopting the McDonald's Speedy system. And it's just providing an overview of the end-to-end chef experience from ordering the food to preparing it and delivering it to the individual or group. And then at the end, you'll see how we'd want to obtain feedback from the customer about the food. And this is for getting that flavor adjustments in the future, because in space, you're limited with the sense of taste and smell. So it'll be good to sort of have that feedback loop to adjust the flavor. And then the dining experience in space, which I would like to collaborate with Kaja and her colleagues with, because it really touches on what they do. And it would focus on togetherness, because these space travelers are far from home. They have each other's company, and people need that social aspect in their life. It will feature the multi-sensory food and flavor perception, which we would bring visual, sounds, and smell into eating the food to enhance their eating behaviors. And it's to encourage people to eat healthy foods and potentially influence a positive experience. And then there's food transformation, and as the name indicates, it's transforming the food to make it enjoyable, and it kind of goes along with a multi-sensory food and flavor perception, but also using technology to transform your food into something more pleasurable to eat. Like if you have vegetable ingredients, you can possibly make that into a cake. So those kinds of transformation. And then there's floating food, which is more of a form of entertainment, which you'd see in a lot of the astronaut videos and pictures online. And it's, you know, eating the food as it floats towards you or away from you, that kind of experience. These are just the opportunities I see. Big thing is definitely the space tourism. But the challenges is, you know, waste management, designing that pressure cooking vessel for zero and microgravity, and also cleaning and sanitizing that kitchen after use. That's been, I mean, still a huge problem in the ISS, where, you know, microbiomes or micro, what is it, biofilms, are sort of developing over the years. So like these germs are becoming more resistant, and they have a buildup on these tubes. Complexities I see are, I would say, understanding the water behavior in a pressure cooker in that microgravity environment, and knowing how food is cooked, what are the emergent behaviors there. But it's really understanding the water behavior with food and pressure. But technologies are advancing, and I think that a fully automated kitchen will definitely be something of a reality in the near future. And that's it for my presentation. Thanks for listening and staying.
Thank you. Thank you, Carla. I know we are now getting ready for dinner.
Yeah.
But you know, one of the things that you may all know is that the person, or maybe even the entity that can cook, is considered the leader in a group of people. And this has been proved over and over in the Antarctica, in forward camps. Folks who can cook can control people. And I think it's a sign of leadership to be able to be a good cook. You know, we are done with all the presentations. I have a few slides I would like to share, if Ken will allow me. Ken, if you can pull up our concluding slides. Oh gosh, okay, well, and we'll take a picture with all these award winners at the end, Ken.
Okay, 1 second.
That's a good one. Okay, good. Okay, so we've heard today, we've heard a whole spectrum of thoughts, ideas. Some of them are concepts, some of them are philosophies. And the beauty of an architectural, a space architectural presentation or a gathering is that we get to hear a lot of different points of view. And this is a hallmark of an architect's education. I wouldn't say you would do this in an engineering school unless you're an open-minded engineer who wants to learn about everything else. But the fact remains that architects and engineers work on exactly the same problem, and yet we have difficulties talking to each other. So Ken, did you want to drive the slide? So great. So to give it a big picture view, like Mark Cohen mentioned, can you go back?
Go back, okay.
So philosophies beget visions, and visions become policies in governments, and then we tend to become the architects and the engineers who develop ideas, show their merits and limitations, and then feed back into the philosophies. So philosophies grow and architectures and ideas grow. And And the most important thing that architects do that I don't see so many of the younger engineers do is tell stories. Storyline matters. How you present matters. And the idea of putting a concept in a concept that is credible makes an entire story different. That's why I like concept and context are connected. And then, I take the risk out of my class by telling my students, work on something that is happening now so you won't have a problem connecting concept to context. Because once you know it's happening and real things are happening, it's easy for us to connect. And so with that, let's go to Ken. Can we have another slide? So visions are not created in a vacuum. And if you ask, is there a space philosophy? We have had some space philosophy gatherings here at the AIAA, and when we do very complicated, complex endeavors, it's very important to have a philosophy in the back of your mind because many times your task manager or your project manager will be faced with questions that are not in the requirements document. And so where do they go? They go deep into their philosophical bend of mind and say what needs to be done. So philosophy leads to vision and to policies, and then everything else we do. And this is true governing all ideologies of great civilizations and projects. So many times when things are not in the book, I think I mentioned this earlier, there's a saying, a heuristic in systems architecting, which says the finest requirements documents are completed after the mission. So it tells you the quandary that you are in. You have this irony of not having all the things in place till the job is done. Let's go to the next one. And so some people make money on this. Simon Sinek goes around talking about why it is important to start asking the question, why are we doing what we are doing before what and how? And sometimes we do it well, but most times we are all in a nebulous mode, hoping that somebody will clarify it for us. Next one. So in terms of space philosophies, there are so many of them in being articulated now, and they all talk to one thing. If you at the end of the day, you say, oh, there are just too many philosophies. Is there any common thread? Let's look at that, Ken. The common thread, let's go, is really this. In fact, we can even focus and say it's about our species. Because Mother Earth knows how to take care of herself. She has done this over 4.5 billion years. But we think that all the space architectural thinking can help in evolving a more sensible, a more frugal, a more relatable way that we engage planet Earth and the biosphere. Next, Ken. So that is why NASA right now has a context. If you think about it, their contextual focus is slowly evolving towards climate change. Our administrator at NASA has been an advocate for several decades, and you will see many more missions flying talking about climate change and monitoring planet Earth. Next. Jim Lovelock, the philosopher scientist who talked about planet Earth being sentient, suggests that the Gaia hypothesis is really about looking at how planet Earth works, and we don't have a handle on it. We really don't have a handle on climate change. We have some loose loose ends and pieces, but we are getting there, and I think space artifacts and space missions will help us to weave a much better picture of climate change. And how do you relate? How do we relate to space activity in climate change? The answer is tough up. We got to tough up, and that is why Lovelock, who passed on recently, he said, "I've always said that adaptation is the most serious thing we can do," which means you got to roll with the punches. And it's happening right now. And I'm thinking that if we use spacecraft technologies, we can be a tougher species. And we can be a tougher species without messing with the planet and without messing with what we call a minimal footprint in the ecology of planet Earth. Next. Now, you may remember Captain Kirk, William Shatner, who just did a suborbital trip on Bezos' rocket ship, and he made a very interesting comment. And this is Captain Kirk, who has been beaming down to different planets all over the universe. He says that the moment you went up, a minute or two or three, he says, down there is light and life, and up pitch black, and what he thinks is death. It's really true, because every single moment you put a human into space, you are dealing with 100% elements that are trying to kill you. And so we do everything we can to experience space. And here is the brave Captain Kirk telling you what it's like to go suborbital into a few miles up into space.
There might be some small businesses who will chapter in this
That's right. Let's go. So, I mean, these are the things. Now, let me tell you something that I find worrisome when architects engage, and it talks to some of the physics that you learned in high school. You know, you want to be thinking about it, and they, a lot of us are scared of numbers. It's not just some of us, but a lot of us are scared for numbers. But arithmetic, everybody can do. And the first and second laws of thermodynamics is something that we got to get used to qualitatively. You don't need to know about how much as much as how. And you'll see that in these first two laws of thermodynamics, which many of them take to heart and cherish for the rest of their lives. Some of them say it is God's way of speaking to us. But that's beyond me. But Ken has run away, so we need somebody to move the slides. Can you push? Okay, good. So first and second law of thermodynamics tell you a lot of things that go on when you exit the cocoon of planet Earth. Can you sit there and do that, dear? And let's go to the next one. So we all know this. Even if you don't know it, you know it from going into a bathtub or taking a shower or coming out or running out into a cold place. You know that there are different modes of heat transfer. But once you exit the cocoon of planet Earth, you're stuck with only one. Can you go to the next slide? And that is radiation. Radiative heating takes over. Everything else becomes subservient to radiative heating and cooling, and it's pretty severe. The heat and the cold is so severe compared to what we experience here, or when you pop into a frozen pool or something like that. It's far more severe. Next, we got radiation too, and the co-author on our book was director of radiation medicine at Palomar Hospital. So he would look at me and say, "Do you know what happens when you get hit with radiation?" And I say, "Yeah, I've read Manhattan Project." No. I mean, has something happened to a human you know. And then he elaborates on how your systems fail and your doctor cannot help you. So this is why we think radiation protection is important. It's very, very important. And so far, we don't have any data directly impinging life and living organisms from space to know how important or whether it's a paper dragon. We don't know. But so that is the main theme of putting people into orbit and on the way to the moon. Let's go to the next one. And if you're in orbit, you know that your system is going to be suffering heat and cold every 45 minutes in low Earth orbit. And the temperature swings are so great that you have to be prepared. Your vehicles have to be prepared with extra energy on each cycle to take care of it when you're cold and then cool you when you're on the sun side. Next. And then you think about going to the moon, it gets even worse. Look at how the temperature swings happen. And if you think, well and good, we'll go down to 89 latitude and relax for a few days. No, the problem is, next. See, if you look at how temperature varies, you get the feeling that you want to be at a place where you got a constant temperature at 50 or 45 Kelvin. Let's go next. And that is where we are struggling with now. We want to put people in the polar region of the moon, and the thermodynamics is extreme with a capital E and capital rest of the letters. It is extreme. And again, next. So energy and action are related. If you have energy, you can do things. If you don't have energy, it happens to animals. That's why iguanas fall from the trees in Florida when it gets cold. They don't have the energy, boom, they fall down. And this happens to us too. If we cool us, we knock ourselves out very quickly. So energy and action are related. In fact, if you look, the Indian philosophies compare both of them together. Energy is one part of the equation and action is the other. And so my thinking on this is, if there is energy, we can work it. We can work anything. If not, we have to really work to find energy. And this is a struggle we are having when we go to the polar regions of the moon. Next. I want you all to think about the triple point. I mean, these are high school things that I don't know if they teach you these days, but high school physics tells you that there is a thing called triple point in all materials. If you put the pressure on the y-axis and temperature along the x, and you put any materials, you'll find that they are vapor, liquid, or solid, depending on the temperature and the pressure. In fact, if you go to Denver, your water boils at 92 degrees Celsius. I mean, so it tells you already that we know these things, but we don't use them. Next one. So there are different things called triple point and critical point that are of interest to us. And then there are different phases. And all of these things matter when you take and play around and mess with pressure and temperature. And it happens in the space environment. Next. That is, you want to read this up. I mean, these are qualitative talks, and it's on, you'll get to see it on Wikipedia. Next. And there is dust. I think somebody brought that up, but you're right. Dust can be messy, particularly when it's electrically charged. Next. And the spacesuits, as we had some interesting discussions, they use a lot of thermodynamics to stabilize the temperature and the ambience inside of a spacesuit to keep the crew member safe and alive. And everybody will tell you that a spacecraft is a small, a spacesuit is a small spacecraft, and it's designed so that you can keep a human alive and operational for a long period of time. And we are struggling now with the new spacesuit, but I'm told that Axiom is doing very well on it. Next. Now, as you all heard in the past a few talks, at least among space architects, we think that human needs are much, much more than what robots need. And that's why we really cling to robots, because we think we can control them, we can do everything, and they don't need food, and they never ask for workers' compensation. You know, so these are the kind of things that we need to get real about. And now, in the last few years, we are understanding that plans make a big difference in human condition in extreme environments. And that is why we are starting to grow food on station, and we think it's very important. Next. So all these things are embedded in the United Nations Sustainable Goals. And that is why the architects drill me every time I'm in the spring semester. They go like, what are you talking about when we know all these things? And I keep telling them that, many of these things matter for people in space and vice versa. Next. So there is space, again, this is philosophical, comes down to us from, I don't know, 5,000 BC or something like that. They differentiated the qualities of the universe as space, energy, air, land, and water. In fact, these are exactly the same things we are fighting about now on planet Earth. Next. So today we had a person who could read that language, but it's called the five spirits: water, fire, air, space, and earth. And these are things that have been debated, not since our grandpa's times, but since since before history. And these are philosophical insights that we need to ingrain in us, even at the qualitative levels. Next. I had asked these nonfiction people from San Francisco to present. They presented a couple of slides at the South by Southwest conference a few weeks ago. And Namfen is also is part of the University of Houston. She's a US 6 grad. And here she says it very clearly, that why we do space is to accelerate innovation so that we can live better on Earth. And that makes very good sense, I think. And a NASA administrator and Pam Melroy, all of them believe this. Next. So, in a word, what would you say? Space architecture is Earth architecture. I mean, it's about Earth architecture being refined in the 21st century, so that we can all appreciate the predicament that our species and the biosphere is in. Next. And these are things that I inscribed on the halls of power. I don't know how many of them will read it, but this one, these things are literally in the parliament buildings in India and in the United States. Can you go back one, Ken? No, forward. Forward, yeah. It's inscribed in the Capitol building. And next. So what are architects known for? We are known for dreaming up visions. And we get into projects in all different areas of project activities: coordination, transformation. But we do one thing differently than from a lot of other professions. That is, I think somebody mentioned it. I think Barbara mentioned it. Barbara Imhoff, and she said, we make beautiful things. We strive for beautiful things. That's why Wolfgang Goethe said, architecture is frozen music. So it is an art to be able to tell a story. And one other thing that an architect does, when an engineer is forceful, when an engineer really burns the midnight oil and wants her or his project done, and she has fire in her belly, there's a thing called persuasion. You call at 2 a.m. Some of you, I don't know, you may know our friend over there, a couple of miles behind in SpaceX. He calls people, at all times of the day because he has a fire in his belly. But we build, I put up that image of Jan Utzon's architecture because the man had a vision. It took many years to build it because we did not have the technology or there were so many politics. But after a long while, it got built. And guess what? It's an icon. Everybody knows the Sydney Opera House. Next. So architects, I believe architects deal more with philosophy and policies more than engineers. But in our school, we realize this. The deans of engineering and architecture have been discussing about what they call engineering plus. The idea is you do your engineering analysis and your math, and then you come into my class and do a little bit of the other stuff, and then you're on your way. Let's go. Now, I want to just finish with 2 slides. This rocket on the left side is the Starship sitting on the booster right now. That is an image from 3 days ago. It's ready to go. It's ready to go, and there's a big difference from all the other stuff you see on the other side, including the Saturn V. You know what's the biggest difference between Saturn V and the Starship? Saturn V is an expendable vehicle, and Starship is fully reusable. A different paradigm in the 21st century. So we are hoping to see this launch. I'm told that notice to mariners have gone out across the globe. So everybody is waiting for this. Elon says 50-50 chance it'll blow up. I think 40-60. But you know what? The moment it's done, the next one and the next one and the next one is ready to come online. This is how engineering is done. I don't know how many of you know this term called pranging. I did this. A lot of people I knew did this. You build something, you break it, and then you know what the heck happened, and you fix it. Anybody who's built, airplane models or flew them, your plane is not going to fly first time. For all the things your aerodynamics is right, you may have even done your equations, now your strokes and so on. But you know what? When it gets to flight, there's a heuristic for it. It says before the flight, it's opinion. After the flight, it's the facts.
I have a question regarding the Starship.
Yes.
Okay, so
let me finish this and then let's go to the next slide. So the things that are coming up, ISDC is coming up. They're hounding me to put up abstracts. Next. That was it. Thank you all, and I'm ready to take.
Thank you, Madhu. So,
can you take a picture of all the guys?
Smile in front of the camera.
Okay. So let's put up a slide so that it looks. Let's put the E pluribus unum slide, please. Oh, can you go back? Back. Oh, that's it. Anything? You like that? Okay. Which slide do you like? You put the slide you like.
Yeah, you want this one? Okay. Sit down.
Oh.
Because the camera.
Oh, okay.
Then we take pictures.
Oh, good.
And show it to the camera. Yes. I take a screenshot.
Yeah, come on this side too.
Yeah. Okay. Yeah. Go.
I have stand up, Ken.
If you stand, you stand there.
Oh, yeah.
Very good, Carl. Thank you.
Anybody else got this? Guys, come on over here. Come on over here.
You two first, then they join.
Look.
Okay, smile. Cheese. 1, 2, 3. One more. 1, 2, 3. Thank you. The rest
go away, you guys. Let's take a group picture.
Yeah, sorry, folks online, we are taking group photos.
And I want Ken to come in. How do we do this?
Why don't you take a photo?
No, you go first.
Go.
Can you take a photo with the one on the tripod?
Yeah, you can put it on the stand and then timer.
I can.
Let's do, okay, don't worry, don't worry. Go. 1, 2, 3, smile, thank you. Oh, 1 second. Two more. 1, 2, 1, 2, 3, smile. One more. 1, 2, 3. Thank you.
Can wait, let me, you can stay right there.
Okay, thank you, everyone.
Thanks, everyone. Thank you online.
Thank you all.
Also, you want to take?
It was a long, not productive day.
Library is closing.
Now, who is that?
It's me.
Oh my goodness, you sat through the whole thing, huh?
Well, it's
Yeah, because library is closing.
okay. So bye. Thanks, Madhu.
Bye bye, Sandra.
Bye. I don't think Vittorio they see us, so it's okay.
Okay. Thank you all for coming in.
Okay, 1, 2, 3. One more.
Bye.
Let's get the flash going. Who else is there?
Going back in time. We're just-
You know, some of us stayed.
Okay,
Hold still for a minute,
cheese.
solid.
1, 2, 3. One more. 1, 2, 3. We'll take one
Oh my
one
God.
with a picture on the top.
They still have to drive, Ken.
Okay. Okay, cheese. 1, 2, 3. One more. 1, 2, 3.
Maybe a flash.
Okay, thank you. Refresh one. Okay, thank you, everyone. Thanks, everyone online. See you next time. We're shutting down, library closing. Thank you.
Oh, I enjoyed it.